So let's get right into it. We all want that amazing, powerful AI, but we want it right here on our own laptops and phones, not just somewhere off in a giant data center. Today, we're going to pull back the curtain on some really clever research that found a secret trick to make exactly that happen, to make AI on your computer ridiculously fast.
It really all boils down to this one question. You can go online and use these mind-blowing AI tools, but the second you try to run a powerful model locally on your own machine, everything just seems to grind to a halt. So what's going on? What's the big bottleneck?
Well, to get it, you have to understand the difference between two key things: AI training versus AI inference. Now, training is the really heavy lifting. That's where AI models learn from just mountains and mountains of data. And yeah, that happens on supercomputers. But inference is what we actually care about on our devices. That's just using the already trained model to get a quick answer, like identifying a person in a photo. For that, you don't need brute force. You need pure speed and efficiency.
So how do we get more speed? The industry's first big idea was this thing called quantization. It's a really smart concept, but as you're about to see, it runs smack into a brick wall.
Okay, so the idea behind quantization is actually pretty simple. An AI model is, at its core, just a massive collection of numbers. They usually start out as these big, super precise 32-bit numbers. Quantization is just the process of shrinking them way, way down, compressing them into a tiny format like 2-bit numbers. The result? A model that is dramatically smaller and, in theory, should be way, way faster. Now, you'd think that by making the numbers that much smaller, you'd kill the model's accuracy, right? But here's the wild part, and you can see it right here in the data. You don't. I mean, look at this. For this ResNet 18 model, when they went from a huge 32-bit version down to a tiny 2-bit one, the accuracy didn't just stay the same, it actually went up a tiny bit. That is an unbelievable trade-off. Okay, so this sounds perfect, doesn't it? A much smaller model, no loss in accuracy. We should be all set. So, what's the catch? Why isn't every AI on your phone already doing this? And here's the wall. Your computer's processor, the CPU, it's an incredible piece of engineering, but it was designed to do math on normal-sized numbers like 8-bit, 16-bit, or 32-bit. It literally doesn't have the built-in instructions to efficiently handle these new, super-compact 2-bit values. So you end up with this hyper-efficient model that your hardware has no clue how to run efficiently.
This is where the team behind DeepGEMM comes in with just a brilliantly simple workaround. Instead of trying to change the hardware, they decided to change the math itself.
And this right here is the aha moment. The whole problem is that CPUs are slow at calculating results with 2-bit numbers. So the DeepGEMM approach just asks, well, why calculate it all? We know all the possible answers ahead of time. So what if, instead of doing the multiplication, we just looked up the answer that we already know is correct?
They do this using something called a lookup table, or LUT for short. And honestly, the best way to picture this is to think back to the multiplication chart you had on the back of your notebook in grade school. If you needed to know what 8 times 7 was, you didn't have to think about it. You just found the 8 row, the 7 column, and boom, there's the answer. A lookup table is the exact same thing, just for a computer.
And this diagram here, it shows that exact idea. The two little numbers that need to be multiplied, they get combined to form an address. That address just points to a specific spot in this pre-calculated table, and the CPU just goes and grabs the answer that's already sitting there waiting. All the hard math is done beforehand, which makes the actual operation incredibly fast. No calculation needed.
But, just having a lookup table isn't quite enough. If you have to look up millions of answers one by one by one, it's still going to be slow. The real genius of DeepGEMM is how it does these lookups at lightning speed.
So how'd they pull it off? Step 1 is super clever. The system takes a whole bunch of these tiny 2-bit numbers and packs them all together. Think of it like neatly arranging a bunch of tiny beads into a single, larger container. You're putting them into one bigger unit that the CPU is actually comfortable and designed to handle. And because all those little numbers are now packed together so neatly, the CPU can use one of its superpowers, a technique called vectorization. Instead of going to that multiplication chart for one answer, then going back for the next one, and then the next, vectorization is like letting the CPU grab the entire row of answers in a single trip. It is a massive, massive efficiency gain. This parallel lookup, that's the secret sauce.
So look, it's a very cool trick in theory, but does this clever idea actually work in the real world? Let's take a look at the numbers.
Oh yeah, it absolutely works. On the MobileNet V1 model, they saw a peak speedup of 1.74 times over the standard method. And let's be clear, that's not some tiny improvement. It's almost twice as fast. That is a huge leap forward.
And you can see that difference perfectly right here. For another really common model, ResNet 50, the standard method, that's QN-NPAC, is our baseline, right there at 1. DeepGEMM just crushes it, coming in more than 1.5 times faster. The gain is just huge and undeniable.
And this wasn't some fluke that only worked on 1 or 2 models. The results were consistently fantastic right across the board. No matter which model they threw at this, they saw these huge speedups, averaging out to about a 1.66 times performance boost. This proves that the lookup table idea is a really robust and widely applicable solution.
So here's the bottom line. The thing you really need to take away from this: DeepGEMM is a software trick that unlocks the true performance of our hardware. It bridges that gap between these super efficient AI models and the CPUs that are already sitting in our computers right now. You don't need to go out and buy a new, expensive, specialized AI chip to get these kinds of speeds.
And that leaves us with a really exciting final thought. A performance jump like this isn't just a small improvement. It opens the door to entirely new possibilities. I mean, what kind of real-time AI applications could we run on a totally standard phone now? How much smarter could all of our everyday devices become when this level of efficiency is just unlocked? That's what makes this work so exciting to think about.